Okay, so welcome to another QSI seminar. Today we are fortunate to have Dr. Kai-Min Chung to give us a talk. Kai-Min is a researcher from IIS, Academia Sinica, Taiwan. He did a postdoc at Cornell after obtaining PhD from Harvard on the supervision of Salil Vadam. And his research is focusing on post-quantum crypto, complexity theory, pseudo-randomness. I guess today he's telling us about delegation of quantum computation with a classical client. If you have questions, please unmute yourself and ask your question. But note that this talk will be recorded and be uploaded to YouTube. Let's start. It's all yours, Kai-Min.
Okay, thank you. Thanks, Zhengfeng, for the introduction and also for inviting me. As you can see, this is my first room talk, so it'll be a special first-time experience to me. If anytime there's anything that's not clear, or if you have any question, or if there's any technical issue come up about the room, please interrupt me, and so that I can feel more interactive. Yeah, so let me start my talk. So I would talk about our recent work on kind of the area of classical verification of quantum computation or delegation of quantum computation. So this is based on two recent papers. One is joined with Naihui and Takashi, and the other is joined with Yi and Hanshen and Xiaodi. Okay, so let me just start by introducing the setting of the question. So let's consider that we have a classical client. Let's call him or she a verifier. And we also have a quantum server. Let's call it a approver. Let's say this classical verifier want to evaluate some quantum circuit on a classical input X. But this classical verifier does not have the quantum power, so she wants to ask the prover to do it for her. So she says, can you help me to evaluate C of X? And the prover says, yes, the answer is Z. But how can this verifier know that the evaluation is correct? So usually we require the prover to try to convince the verifier that the computation result is correct. So they engage in potentially interact proof, communicate for a few rounds, and at the end, hopefully the verifier will be convinced that the answer Z will be correct. So this question is first asked by Gottesman in 2004 about can a classical computer verify the result of a quantum computation, maybe through interaction. So this is a very interesting theoretical question, but it's also I think very motivated nowadays given the advance of quantum computation. It's foreseeable in the future, near-term future, that even if quantum computer is built successfully, it will be a giant computer sitting in the cloud, and us classical users would only be able to access to those quantum computers on the cloud. And we would, of course, want to make sure that our computation done in the cloud is correct. So for this question, a simple answer comes from complexity theory is to use this result by Shamir on IP equal to P space. Since PQP is inside P space, so we can use a general interactive proof for P space to verify the computation result of the quantum computation. However, the issue is that in order for the prover to proof using this generic interactive proof, the prover would require to have a p-space computation power, which is potentially beyond the BQP prover. So the question is whether we can achieve this goal to allow the classical verifier to verify the computation of the quantum server with also the prover also run in efficient polynomial time with polynomial quantum computation. So throughout the talk, I would use T to denote the circuit size and also the time complexity for the quantum computation to be delegated. Okay, so this question has a long story since 2004. So for a while, people don't know how to construct such a protocol with a classical verifier and also a single quantum server. So two relaxed model has been considered. So the first model is to allow the verifier to have some weak quantum power. So the verifier may be able to process, compute, or measure on a small number of qubits. And in this model, there are several solutions starting from broadband DL. And in another relaxed model, people consider a classical verifier, but we let the verifier to interact with multiple non-communicating but entangled prover. And the first result in this model was achieved by the work of Richard Unger and Vizrani. And then also there are a sequence of follow-up work that try to improve the efficiency and also reduce the number of prover. Okay, so kind of recently, 2 years ago, this question was finally solved by important work of Mahadev, who showed the first full-round classical verification of quantum computation protocol with purely classical verifier and a single quantum server. And her protocol is for decision problem. So we can view it as the prover tried to prove input statement X is in a BQP language L. And the protocol consists of 4 rounds. So by 4 rounds, I mean the verifier and the prover exchange 4 messages in total. And at the end, the verifier will just accept and reject. And the protocol would require a computational assumption. Based on a by now quite standard assumption that learning with zero problem is hard for polynomial time quantum computer. So in terms of running time, both the verifier and the prover are efficient. So suppose this language L can be decided in time t for a quantum algorithm, then both the verifier and the prover's running time will be polynomial in t. One kind of drawback of Mahadev's protocol is that this protocol would have a large sounding zero, a large constant sounding zero. So the sounding zero will be a half plus some negligible term. Okay, so in this talk, I will going to kind of present several of our improvement or generalization to Mahadev's protocol that mostly motivated by kind of the general Desiderata when we consider kind of classical client who want to dedicate computation to a quantum server. So let me now describe the first contribution we do. So the first one is to address this issue of large constant sounding zero. So we show that we show a parallel repetition theorem for Mahadev's protocol. we show that M for the parallel repetition of Mahadev protocol would reduce the soundness error to 2 to the minus n plus some negligible term. So this seems to be quite expected, especially if we consider some independent event. Then, of course, M independent event would bring down the probability exponentially fast. However, parallel repetition is in general quite tricky to analyze for the computational setting here. And in fact, there are classical counterexamples showing that there exists some full message protocol, like Mahadev's protocol, such that parallel repetition would not decrease the soundness error of the protocol. So this is not generally true, but for Mahadev's protocol, we are able to rely on some special property of Mahadev's protocol to show that the soundness error indeed decrease as if the repetitions are independent. So this is kind of the first non-trivial parallel repetition theorem in the quantum or post-quantum setting. And let me mention that it's an interesting open question to consider parallel repetition theorem for 3-message or public key protocol in this post-quantum setting. So for both classes of 3-message protocol or public key protocol, parallel repetition is known for classical interactive protocol with computational soundness, but it seems to be quite difficult to analyze in the quantum case. So let me also mention that independent and concurrent to us, Allegio and Charles and Brillo and Hong, they have independently proved the same parallel repetition theorem, but interestingly with a very different proof from us. I will comment on this later when I talk about this result in detail later. Okay, so now we have kind of reduced the soundness error to negligible using parallel repetition. Now we can ask what other Desiderata do we want for such a classical verification of quantum computation protocol. So I think a very kind of nature and kind of well-motivated question is to consider delegation of quantum sampling problem. So instead of only consider delegation of this decision problem, the delegation for PQP, it's very natural and very well motivated to consider a delegation for quantum sampling task. And there are a few kind of obvious reasons. First, quantum mechanics is intrinsically random, and also if you think about it, many, if not all, quantum algorithms and tasks are about generating randomized outcomes. So for example, kind of famous quantum supremacy experiment, it by nature is a sampling problem. And also many algorithms in the context of quantum machine learning and optimization usually generate some randomized outcome or randomized model. And also, even for like algorithms for classical function like Shor's algorithm and Simon's algorithm, the main quantum routine, like quantum Fourier transform, also generate randomized outcome. And the algorithm goes by combining those randomized outcomes with some classical post-processing to kind of compute the final answer. So if we want to just verify the core computation of Shor's algorithm and simple or Simon's algorithm, we will also need to consider a problem of verification for quantum sampling power. So informally, the goal would be for a classical verifier to learn a sample Z from a computation of a quantum circuit C applied on X with correct distribution from a potentially untrusted prover. And we should have the guarantee that when the verifier accepts, the verifier would be confident that this distribution Z will come from the right distribution. So while this problem is quite natural, it's somewhat maybe a bit surprising that the problem seems to be not considered before. So previous work on the CVQC seem to always focus on decision power. As we'll see more later, the challenge seems to be the difficulty of letting verifier to learn a sample Z instead of just a bit. And we also need to ensure that or reason about that the sample Z to be the right distribution. And also for sampling problem, unlike the decision problem, it is unclear how to amplify its correctness by repetition or taking majority vote. So as our second result, we construct the first CVQC protocol for quantum sampling problem. So we build on Mahadev's protocol. So our protocol is also for round or for message. And when the verifier decides to accept, the verifier would also output a sample Z of the computation result. And we also build based on the computational assumption that the learning with zero problem is hard for quantum polynomial time. So in terms of the runtime, both the verifier and prover runs in polynomial time in the complexity of the circuit. So in terms of soundness, more precisely, what we can show is that for any given inverse polynomial epsilon, if the verifier accepts with probability greater than this noticeable epsilon, meaning that the verifier will not almost always reject, then conditioning on this accepting event, the verifier would know that the output sample Z that should generate will be close to the right distribution of the sample from C of X. And here, since we are in a computational setting, so this closeness will be a computational indistinguishability. Okay, so let's move to the second Desiderata, which has also been studied in the literature, which is called the blindness. So blindness means that the prover should help the verifier to do the computation, but not learning any information about the verifier's private input X. So this is a property that is studied and achieved in the relaxed model, and also recent work of Gelgu and Vidic. They also extend they also consider this CVQC setting and construct the first applied CVQC protocol for BQP. Using a kind of a different approach from Umina's protocol. But their protocol would require a polynomial number of blocks. And also the proof is quite involved. For this Desiderata, our construction is, our contribution is very simple and a generic blindness compiler. So we show that there's a compiler that can compile any CVQC protocol to achieve blindness while preserving its round complexity, its completeness, and its soundness. So applying our compiler directly to Mahadev's protocol, we will get the first constant round blind CVQC protocol for BQP. And our compiler also applied to our protocol for the content separately problem. So we will also get a constant round by the CVQC protocol for content separately problem as well. Okay, so finally, the last Desiderata I'll talk about in this talk is about the verifier's complexity. So far, we talk about delegation protocol where both the verifier and the prover need to run in time polynomial in T, the time complexity of the computation when the delegate. And the verifier is saving in terms of content resource. The verifier only need to run in classical poly T time instead of quantum poly T time. However, if we compare to the classical delegation of computation literature in cryptography, in the second layer, it is a mandate requirement that the verifier should run in time equal O of T. Since in the classical setting, the verifier also has the ability to perform the computation by herself. So if the verifier's runtime to verify the computation is omega T, then the verifier might as well just perform the computation by herself. So in the classical setting, it is a necessary requirement for the verifier to save in the verification time. So in the classical literature, there's also a long line of research that allows the verifier's time to reduce to pretty close to linear in the input length, independent of the time complexity of the function. And for the prover side, the prover can also be pushed to almost linear in T, the time complexity of the delegated computation. So in the content setting, of course, this will also be a desired feature. For example, we may want to delegate a heavy content computation from our cell phone, which may be a weak device that may not be able to even perform a poly T time classical verification. But this seems to be a challenging goal, and the difficulty related to the lack of content PCP theorem. And this is because in the classical literature, most of those work rely on some form of PCP machinery, and there are also converse results showing that this kind of verify efficient delegation protocol would also imply a certain form of a PCP theory. But in the content setting, because the lack of content PCP, for I think all the kind of existing work in the literature, the verifier would require to run in poly T time, even in a relaxed model. Actually, I talked to Zhengfeng by email a few days ago. It seems plausible that from this recent line of work to get MIP star equal to RE, there the verifier is indeed a classical verifier with a fixed polynomial time, but the verifier can verify a statement with very high complexity. So there it seems to be possible for the verifier to run in time sublinear in T, but one thing that's not yet very clear is whether for the case of BQP, whether the prover in underlying this result would also run in polynomial time, content polynomial time. And maybe Zhengfeng can give a further comment after my talk. Okay, so our last contribution is also the first CVQC protocol with efficient verification. So in particular, the running time of our verifier would be polylogarithmic in T. However, a kind of big caveat is that in our solution, we kind of throw in very heavy kind of crypto machinery. So our result is based on kind of very strong cryptographic assumption. So we view this as mainly a feasibility result, showing that it is kind of achievable in certain model, but it would be really nice to obtain such a result with weaker and more reasonable assumptions. So given that we already saw in very heavy machinery, we additionally get a 2-message protocol instead of 4-message protocol, and we also get negligible soundness error. Okay, so here is a summary of our result. So just to quickly repeat, we prove a parallel repetition theorem, and we show how to extend the CVQC for decision problem to content sampling problem. And we show a generic blindness compiler to turn any protocol, CVQC protocol, to achieve blindness. And we also show that using heavy crypto tool, we can make the verifier efficient, running time polylogarithmic in the time complexity T. So in the rest of the talk, I guess this is not a particularly crypto crowd, so I will not try to kind of throw too many kind of cryptographic construction to you. So I will try to focus on the first 2 results and try to keep high level on the construction to just give you a high level idea. So I would first talk about a high level kind of overview of our protocol for content sampling problem. And then I would try to get into some technical detail to talk about the proof of our parallel repetition theorem, which I think use some interesting result from kind of like QMA amplification, which would not need too much background from Mahadev's original protocol, and I hope that part will be kind of interesting to the audience. And for the rest 2 contributions, I will just briefly mention that the construction for the blindness compiler uses content fully homomorphic encryption. These are encryption schemes that allow to homomorphically evaluate content computation under the encryption. So the idea is quite of nature. We just need compile the protocol to run the original protocol under a layer of content FHE. This will allow us to maintain the functionality of the protocol while get the privacy. But there are some subtleties in the ways to kind of run the protocol on the content FHE in the right way, and also a little bit of subtlety in the security. And for the CVQC protocol for efficient verifier, I will not talk much. I will just kind of show you that these are all the machineries we need to make the verifier efficient. And the high-level idea, again, it's quite nature, is just try to delegate the kind of classical verification task again to the content prover, but here the verifier is not only heavy in the computation, but also heavy in the communication. The communication complexity of Mahadev's protocol would be also poly in T. So to compress this communication to make the verifier time independent of T is the main kind of challenge and the main reason that we need such a heavy crypto tools. Okay. Okay, so let me move on to talk about the CVQC protocol for content sampling problem. And in order to talk about this result, I need to kind of give you a very high level overview of Mahadev's protocol, and then tell you how we kind of build on and modify it. So Mahadev's protocol is, I mean, at a very high level, is actually a compiler that compile weak content verifier protocol for PQP by Morima and Joseph Fitzman to one that require only purely classical verifier. So the main kind of core construction of Mahadev's protocol is something called the measurement protocol that I will describe in the next few slides. But at high level, Mahadev take this weak verifier protocol, weak content verifier protocol, and apply it to combine with this measurement protocol, and this will yield the final CVQC protocol for PQP. So let me talk about each of these building blocks in turn, again, at very high level. Okay, so this weak content verifier protocol is called the Post-hoc verification protocol, and it actually consists of only a single round as follows. So the prover would prepare and send some content state psi x, depending on the input x, and prover will send it qubit by qubit, since the verifier is a weak content verifier. So the verifier would also process those qubit by qubit. The verifier will apply X over Z measurement on each qubit. And the verifier can do so immediately after she receives each qubit. And so the verifier only need to have the ability to kind of process a single qubit and only need to perform XZ measurement on each qubit. And then once the verifier learns the measurement outcome, the verifier can decide accept or reject based on her measurement choices and also the outcome W. This protocol would also has negligible completeness on this error. So given this such a protocol, Omega will compile it using a measurement protocol. So what does the measurement protocol do? So at high level, we see from the previous slides that the verifier kind of mainly need to learn this measurement outcome W. Let me go back. The verifier only need to learn this measurement outcome W in order to make her decision. So this measurement protocol is a way to allow the verifier to learn a measurement outcome of some prover's content state, like what's needed in the previous protocol. So basically, this protocol allows the prover to commit to some state and let the verifier to learn the XD measurement outcome of the state that the prover commit to. So in the first two messages will be the commit phase, where the verifier will generate some public key and store some secret key. And then the prover will use this public key to generate a commitment Y. And this commitment Y would kind of let the prover to commit to certain state side. And then in the kind of third message, the verifier would just give a 1-bit C. This bit will indicate whether the verifier wants to do a test round or do a hard round. And the verifier will send a uniform union C. Then, depending on the value of C, the prover will give some answer. And for the test round, the verifier will just check the answer and kind of test this commitment and decide to accept or reject. And in the hard round, the verifier will be able to learn this measurement outcome W from this prover's answer A and also the secret key K. And the kind of the main property of this measurement protocol is that if the prover can pass the test with high probability, then this commitment should be binding in the sense that indeed this W learned by the verifier would corresponding to the measurement outcome of some state psi for any measurement choice that the verifier chooses. Now, given this measurement protocol, it's kind of very straightforward to combine the two protocols we just see. So basically, Mahadev's CVQC protocol would be running the measurement protocol to let the prover commit to the content state in the post-hoc verification protocol. And basically, in the hard round, after the verifier learns the measurement outcome, the verifier will decide whether to accept or reject based on W and her measurement choice. By the way, this measurement choice is encoded in this PK and SK. Yeah, so kind of at very intuitive level, the intuition for soundness is then that for the case where X not in L, then either the prover would fail the test, or the prover can pass the test, but then this commitment is binding, and then the soundness of the post-hoc verification protocol would make the verifier reject in the hard round. And we will get into a bit more detail later for this part. Okay, so let me try to give some high-level idea about how to kind of extend this protocol to handle content sampling problem. So we need to kind of open up the box and kind of modify the underlying post-hoc protocol in the first step. So we generalize this protocol to handle content sampling problem. And then we can also apply, compile it with this measurement protocol to get a protocol, candidate CVQC protocol, but that protocol would not immediately work. So here we would need to apply a parallel repetition, some variant of parallel repetition in order to make it work. And this will be the kind of most technical part of the analysis. Okay, so now let me again talk at high level about how to modify this post-hoc verification protocol for BQP to extend it to handle content sampling problem. So to do so, I need to then open one more layer of box to talk about the structure of this protocol. So this protocol is mainly by applying this local Hamiltonian technique to verify this computation of this BQP algorithm. So basically, this state psi x is just the history state of the computation for deciding this BQP language L. And this XD measurement outcome would be to estimate the local Hamiltonian energy of the local Hamiltonian for this language. If we only use one single copy, then this local Hamiltonian will only have very small inverse polynomial energy gap. So to amplify the completeness and soundness, we need to use the repetition to amplify the gap. So this is kind of the high-level structure of this post-hoc verification protocol. So how do we modify it to handle content sampling problem? So first of all, in this local Hamiltonian for BQP, there will be a Hamiltonian to measure kind of the outcome of this BQP decision algorithm, output 0 or 1. But here, we are in the content sampling case, so the input is a content circuit C and X, and the output will be, say, the first K bits or first M bit of C of X, measured in computational basis. So we would need to output the multiple qubit. So we cannot just encode this multiple qubit in some kind of energy of some local Hamiltonian. So the way we do it is then we just use the Hamiltonian for the circuit part to kind of to encode this history state in the ground state. And in order to get the output, we will simply just measure this psi x. However, and we will know that if the clock register is equal to t, then we will get the kind of the measurement of the final state, which is the outcome of C of x. But that would only happen with low probability. So a simple trick would be just to pad this circuit C by adding a bunch of dummy gates. And by doing so, if we measure on this history state, then we will learn the outcome of C of x with decent probability whenever this clock register has value greater than t. However, going back to this local Hamiltonian, so here we do not have, we are not using this ground energy to kind of distinguish the yes instance and no instance of the computation, but we are using this ground energy to kind of certify this ground state, this history state. So in order for this to work, we would instead require a spectrum gap between this Hamiltonian, this ground energy of the Hamiltonian and the excited energy of Hamiltonian. So this will be a somewhat different requirement from the usual local Hamiltonian reduction. However, this is this actually already done in another context. This is reminiscent to adiabatic simulation of content circuit. So we can kind of use the technique built from there. Here we still need to tweak a little bit in order to make in order to restrict the verifier's measurement to XD measurement, but this could be worked out properly. And now the kind of the next issue is to amplify the gap. And here things become a bit more trickier. So here, as mentioned, we will measure this history state to read out the output of C of X, but we will also use need to use this comput'n state in order to estimate the energy. So to do both, we use some nature cut and choose protocol where we require the prover to send multiple copies and use some of the copy to kind of test the energy and use some of the copy to read out the output. Here, the analysis is a little bit subtle since there could be arbitrary entanglement among the state in different copies. And here we need to use definitive theory to handle it. So both steps are not too bad. And by doing so, by doing this modification, we will get a post-hoc verification protocol for contents and pooling power. And then we can apply measurement protocol Mahadev to compile this protocol we have and see what we get. So let's just maybe go over it one more time to see what happened. So in this measurement protocol, the verifier would send a public key and maintain a secret key. And prover will use this public key to commit, to send a commitment Y that commit to some content state, hopefully the repetition of the history state in the previous construction. And then the verifier will choose to test or do Hatam around, and the prover will send an answer. Now, the verifier in the test run can only test whether this commitment is correct or not. And in the Hatam around, the verifier will read off the measurement outcome and use it to estimate the energy and also to generate the output of C of X. So everything works out. I mean, functionality-wise, everything works out. But as we can see, if the verifier chooses to do a test round, which happens with probability 1/2, then the verifier would not be able to learn a measurement, not able to learn an output sample, even if the verifier chooses to accept. So unlike in the case of decision problem where we can still get a soundness level 1/2, applying measurement protocol to our post-hoc verification protocol would not give a very meaningful guarantee because of this issue. So instead, in order to kind of make sure we can get the output sample, we can always let the verifier get the output sample. We would use another parallel repetition, and we would let the verifier and prover to intact in M parallel copies and use the M-1 copies to do the test round and use the random single copy to do the Hatam round in order to generate an output. So the construction is still fairly nature, but the issue is to analyze this parallel repetition and to make sure that when the verifier accepts, indeed the output sample, the verifier then from the Hatam round would have the correct distribution. Okay, so I guess I won't have too much time to talk about the parallel repetition theorem, so I will just quickly go through it and see if I can convey at least some of the high-level points at the inside. Okay, so here is just to show you the parallel repetition protocol more explicitly. So in this parallel repetition protocol, we'll let the verifier and the prover run the protocol and copy of the protocol in parallel. So every message is blown up to n independent copies. And at the end, for each copy, the verifier would perform its test or verification depending on if it's a testing round or a Hadamard round. And then at the end, the verifier would only accept if all the repetition accepts. By the way, we are moving back to the BQP setting. And the claim is that this parallel repetition protocol would have soundness equal to minus n plus negligible. So I think given the lack of time, I would probably skip most of it. I think I will just skip the older analysis, but maybe just tell you why the problem is non-trivial at very high level. So here, when we try to analyze the soundness of this parallel repetition protocol, the main difficulty is that a malicious prover may not choose to run each of the repetition independently. The prover would kind of correlate or entangle his strategy in an arbitrary way. So, kind of the soundness error would not follow by just analyzing each repetition separately. We need to kind of consider them together. Okay, so these are the technical part that I won't have time to go through. So I would just skip them all. And let me maybe just mention in a few words about a comparison to work of A.Sinica and EL. So I unfortunately don't have time to talk about the proof, but let me still compare it. Let me mention that in their proof, they actually give a much simpler and elegant proof than us. And in particular, in our proof, we spend a lot of effort in order to construct some efficient projector to this two subspaces we defined, and they avoid all this complication at all. But on the other hand, our analysis, even if we have done this heavy work and make the proof more kind of constructive, our analysis become more versatile, and in particular, to analyze the parallel repetition of our CVQC protocol for the content sampling case, such kind of efficient projections seem to be necessary, and it's not clear how to extend their analysis to the content sampling. Okay, so So let me, I'm almost running out of time, so let me just summarize. So I'll list the things we have done again. And I will not repeat it again, but I will just mention some of the open questions that I think is important given the state of the art. So one question I would like to highlight is about efficient verification. As you mentioned, this seems to be quite difficult, and we do it using kind of very heavy crypto machinery. And also our work, our construction only work for the decision problem. Okay? So efficient verification will be open for the contents encoding problem, even if we are willing to throw in heavy crypto machinery. So the first will be the feasibility question about getting efficient verification for contents encoding problem. And also, we use very heavy crypto machinery, so whether we can get a weaker, get it from a weaker assumption, or in a relaxed model, in particular where this MIP star equal to RE result, whether we can extract efficient verification protocol for BQP from this MIP star equal to RE result. And also in general, the protocol I present today are actually all quite inefficient. So the prover and the verifier's runtime is poly T, but this poly T is maybe this T to be fifth or larger. I think no one has tried to optimize this this complexity yet. But for this kind of CVQC protocol to be useful, this would be kind of a necessary step to move forward. In particular, in principle, this kind of CVQC protocol would be useful to verify content supremacy, but clearly, given the complexity of the prover in such a construction, that would not be useful for a near-term verification. So this improving the efficiency is another kind of important question. So that's it. I'll just end my talk here.
Thanks, Kai-Min, for the great talk. I guess a lot of materials good enough for 2 talks at least. So do we have questions? Can you go back to the only technical part that you showed us, the quantum sampling procedure, like this history state construction there?
Oh, okay. I think you refer to this slide.
Yeah, this one. Yeah, I'm trying to understand the idea, like a basic high-level idea. We still have a history state. Now it's a sampling problem. So what are the dummy states? Are there identities?
Yeah, the dummy gates are just identity.
Okay. Okay. And so why do you need this dummy gates?
So the way we kind of read off the output is by just measuring this history state.
Mm-hmm.
And we just hope that the clock register will give us a timestamp that's corresponding to kind of the final state that where the computation is already finished.
Mm-hmm.
So without padding, then this will only happen with probability 1 over t.
Okay.
But just by a very simple padding, say pad t prime equal to, I don't know, t squared, then we will get the output with probability, with high probability.
So which output you're talking about? Like you're measuring all this in output qubits, right?
So here the kind of
that is the state part, right?
yeah, there's a computation part where the computation part will encode the final state of the computation, and by measuring them in computational basis, will give us the output of COBs.
How do you enforce correlations? It's not like measuring different copies of the history state. It's a single history state. You measure all this basis measurement on this and output qubits.
Yeah. So so basically what we will do would be the following. So we'll ask the prover to prepare a large number of repetition, and we will randomly choose one copy for output, and we will use all the other copies to estimate the energy of the Hamiltonian. So if the energy is pretty close to the ground state, then we kind of believe that the copy we are using for the output would be also close to the ground state. So when we measure it, we will get a output sample with the right distribution. That's the intuition.
Xiaomin has a question.
Yes, Kai-Min. Yeah, it's a really nice result and a nice talk. So unfortunately, you do not have time to mention the contribution 3, the generic blending compiler. My question is, for the blending part, do you need any further assumption, or is still, I mean, the LWE is already enough?
Yeah, LW is already enough, and the reason is that we only need to use labeled content FHE, which can be implied by standard content LW assumption.
Okay. Okay. Thanks.
More questions? Do you have any opinions on CVQC without crypto assumptions?
I think there's some barrier result by Scott Harrison, Kashafi, and a bunch of other essays I don't remember. So there's some complexity barrier to achieve, I think, classical verifier, single quantum prover, CVQC with information theoretical soundness. I don't remember if they require blindness.
Yeah, I guess they have a lot of conditions, so but like you can relax any of the conditions to still have any possibilities that you have results without any crypto assumption.
I see.
Or maybe to crypto people, it doesn't really matter.
Yeah. So yeah, and then I was thinking it would be also very interesting target to study.
Any more questions?
So maybe let me ask Zhengfeng about.
Oh yeah, the delegation. Yeah, I guess it should be possible using the techniques in our paper. Like you cannot use it like in a black box way because we talk about Turing machines and it doesn't work well when you have input and running time that are separate. But like using the ideas should be possible.
So you mean that you don't necessarily need to start from non-deterministic class. You could stuff.
Yeah, I guess like the barrier you mentioned, you don't have quantum PCP theorem, but sort of you can use, at least in the two-player model, you can use quantum soundness of the PCP functions. So yeah, basically, or maybe another way to think about it is once you have a classical verifier, you can delegate this verifier a second time. There are a lot of more provers you can do this, right? And even you can merge the provers. So I guess like, well, the answer should be definitely yes, but like whether it's a simple way or it's some technical difficulty, I'm not quite sure.
See.
Okay, if there are no more questions, let's thank the speaker again. Thank you for coming to the talk today.